Looks good, huh? All right, let's do more eigen stuff today. In particular, the diagonalization. So you remember if V is an eigenvector of a matrix A, which is a square symmetric. Sorry, not symmetric. Symmetric will be in the next lecture. It's so automated to say square symmetric. No. It doesn't have to be symmetric. We didn't even discuss symmetric matrices yet. It's a real square matrix, and V is an eigenvector if A times V is equal lambda times V, where lambda is the corresponding eigenvalue to the eigenvector V. That's what we were discussing the last time. We were also saying that sometimes we cannot get away just with real eigenvalues and eigenvectors. Sometimes we need to go to complex, but it doesn't really change all that much, except that we have to think a little bit more complex. And one of the interesting things is that then if we repeatedly apply the matrix, and I'll show an example how this is useful, by one particular application where we will want to do exactly this, when we want to be applying the same matrix over and over again, and instead of doing the matrix vector product, in case V is an eigenvector, all you really need to take powers of is the eigenvalue, because A times V, because V is an eigenvector of wave with eigenvalue lambda, then if you just repeatedly apply A, that means just repeatedly scaling the eigenvector V with the eigenvalue lambda. So it works for like any power you take. It could be K, could be like 1,000, could be million, and it's still just multiplying by a scalar. The scalar is raised to the power. Okay, and the point now will be to use eigenvalues and eigenvectors for diagonalization. So this is again like a precursor to SVD, but it's already getting almost there. So this will be related to eigenvalue decomposition. So what we will need here, however, is for the matrix to have a full set of eigenvectors. What do I mean by a full set of eigenvectors? I mean, if I have an n by n matrix, I will want n linearly independent eigenvectors. If I have that, then I can diagonalize. And I think it works the other way around too, that I can diagonalize if and only if I have a full set of eigenvectors. Now, sometimes that does not happen, and I will show you some examples where even the complex numbers don't save you, that the matrix just will not be diagonalizable even in the complex domain. But in many important cases, this can be done. So one particular case which guarantees diagonalizability or whatever is that you have unique eigenvalues. By unique, I mean if you make a list of the eigenvalues, that there will be nothing repeated. I mean, if you find the roots of the characteristic polynomial, sometimes the roots can be repeated, right? We know from the fundamental theorem of algebra, which is neither fundamental nor of algebra, but it's true, which says that polynomial of degree n has n complex roots. And sometimes they can be real, right? But it doesn't say anything about how do they repeat, right? Like if I take a polynomial like this to 100, this polynomial has to have 100 roots because it's degree 100, but they are all 1, right? So the roots are just all 1s. So those are repeated. If this was a characteristic polynomial of some matrix, those would be repeated eigenvalues. This theorem, this part, this is what I will want to show you, this part of the statement, is that if this is not the case, if the matrix has unique eigenvalues, meaning that if I sort them, that there are no two eigenvalues are the same. That like they are nice. Every eigenvalue is different from every other eigenvalue. So let's prove this. It's sort of nice proof. Not super difficult, not super easy. Just a piece of paper for that. Let's prove it on a separate paper. So what is the situation? We have a matrix which is a real n by n matrix, and we are saying that x1 to xj can be any number. J is of course less than n, but that's not the point here, are eigenvectors with eigenvalues lambda 1 to lambda j. And the important thing is such that, do you use this like for such that? Okay, good. Such that lambda I is different from lambda j for each I different from j. So this is my way of saying that all of these eigenvalues are unique. That it's not the case that there will be the same number repeated twice or 3 or more times within the set of eigenvalues. So then the statement is that then, and this is a very nice, elegant statement, are linearly independent. So let me say it one more time, just in plain English. If I have eigenvectors corresponding to unique eigenvalues, then these eigenvectors are automatically linearly independent. So this links eigenvectors and what we were talking a lot about before, the subspaces, linear dependence, and independence. So why, or how do we prove that? I don't think it's obvious at all. So to prove that vectors, so let's start with a simple case where I have just two eigenvectors corresponding to two different eigenvalues. So let's start with that. It's always a good idea to start with a simple case. So what I need to prove, so when are two vectors x1 and x2 linearly independent? Well, that's if and only if this equality implies equals 0 as a vector. That implies that both C1 and C2 have to be zeros, right? That's how we define linear independence. If I take a linear combination of the two vectors, which is 0 vector, that can only happen if both of these are 0. Only the trivial one will do it. That's how we define linear dependence, linear independence. If they are linearly dependent, then I can find a non-zero combination of the two vectors. Remember that? It was in your test. So how do we prove that? So we start with this, and we need to prove this if they are linearly independent. So we take I take x1 and x2, which are eigenvectors of A. And I assume, and I take some linear combination of them, and I want to prove that from this follows that C1 and C2 must be 0. So I know this, right? I know that C1 x1 plus C2 x2 is the 0 vector. And what I can do, I can multiply it all with A, right? I can do that because if I multiply equality by 0, of course A times 0 has to be 0, right? So I start with this. So yeah, the assumptions I started, the proof is this one, and the fact that x1 and x2 are eigenvectors of A with eigenvalues lambda 1 and lambda 2. Make sense? So from this follows that if I multiply it by A, then obviously it is still 0, right? But then I can use the fact that x1 and x2 are eigenvectors of A. So that means that this is true, right? Because axi is lambda I xi. That's the definition. That's what it means for xi to be an eigenvector with eigenvalue lambda I, right? So this is what I got. But on the other hand, if I start from this and I just multiply it with lambda 1, then I get this. C2 lambda 1 x2 is 0. So I have these two equations. And now look, I can subtract them, right? If I subtract them, the first term, this one, it just falls out because it's the same in both of them. And what I get is C2 times lambda 2 minus lambda 1 x2 equals 0. I just subtract, so I took this equation and I subtracted it from this equation. It's a vector equation, but it's fine, right? So this one is the same, so it just subtracts to nothing, and this C2 x2 is repeated, so all I get here is lambda 2 minus lambda 1, right? And now comes the assumption, this assumption here, this one, that they are different. That lambda 2 minus lambda 1, that is not 0, right? And x2 is not a 0 vector either. Why is x2 not a 0 vector? Because it's an eigenvector, right? And I said that eigenvectors by definition cannot be 0 vectors. So this is non-zero, this is non-zero. This can only be true if C2 is 0. Right? So this gives me that C2 must be 0. And to get that C1 must be 0, all I need to do is multiply this by, take this equation, this one, and multiply it by lambda 2, and I will get C1 lambda 2x1 plus C2 lambda 2x2 is 0. Now I can again subtract from this equation, and I will get this. Lambda 1 minus lambda 2 x1 is 0. And that's exactly the same argument. Now gives me that C1 must be 0. So both C2 and C1 are 0. So this verifies that indeed x1 and x2 must be linearly independent, because their only linear combination that gives me 0 is the trivial one, is the one with C1 0 and C2 0. Or the other way around, if I found some non-zero C1 and C2 that gives me 0, I would get a contradiction, whatever way you want to twist the logic. Okay, did you follow that? So now we can try the general case when I have j of them. The idea is really the same, right? If j is not just 2, the idea is similar. So now I have to prove that from this assumption, it follows that all of the coefficients are zeros, right? And the way I do it is, and again I have these x1 to xj's, those are eigenvectors of A with eigenvalues lambda 1 to lambda j, and I assume that they are all different. So the first thing I do, again, I multiply the whole thing with A. So this obviously gives me that C1 lambda 1 x1, then there is some C2 lambda 2 x2, and so on, right? To Cj lambda j xj is 0. And I'm essentially applying the same tricks as before. So then I can take this, that's my assumption, and multiply it with lambda 1. C1 lambda 1 x1 plus C2 lambda 1 x2, and so on, until Cj lambda 1 xj is 0. So I took this equation and multiplied all with lambda 1. I can do that, right? And then I can subtract these two. And what do I get after subtracting them? I get C2 lambda 1 minus lambda 2 x2. Then there would be some C3 lambda 1 minus lambda 3 x3, and so on, up to Cj lambda 1 minus lambda j xj is those are all supposed to be vector zeros. Yeah. So this way I eliminated the C1. That's what happened there. It's a little bit technical, but the key ideas are relatively simple. I'm basically just eliminating the coefficients, the unknown coefficients C's. And now I need to just apply the same tricks one again. So I can multiply this entire thing by A. So I will just do it a little bit quicker now. So by multiplying with A, I get here lambda to x2, right? C3 lambda 3 lambda 3x3 and so on. J lambda 1 minus lambda j lambda j xj gives me 0. And now guess what? I can also multiply it by lambda 2, which gives me this. Lambda 1 minus lambda 2 lambda 2x2 plus c3 lambda 1 minus lambda 3 lambda 2x3 and so on. And now all the terms are being multiplied by lambda 2 now. Lambda 2xj is 0. Visible? Oh, the focus is ideal. Let's see. Oh, it's probably as good as it gets. And now guess what? Now I subtract them. So I will get C3, and what is the coefficient here? It's lambda 1 minus lambda 3, lambda 2 minus lambda 3, x3. And there it continues up to some Cj, lambda 1 minus lambda j, and lambda 2 minus lambda j, xj is 0. So you can be guessing what would follow. Essentially, I can keep eliminating and eliminating until I eliminate myself until this expression. Lambda 1 minus lambda j, lambda 2 minus lambda j, and then it will be like lambda 3 minus lambda j, and so on, up to lambda j minus 1 minus lambda j xj is 0. And then I know that all of them are different, so all of these guys must be non-zero. That's non-zero, that's non-zero, that's non-zero. This is eigenvector, so it's also non-zero. So again, similarly as in the simpler case, from this follows that it's the Cj that must be the 0 there. And I'm not gonna do all the other cases, otherwise we would spend a whole hour just by doing this. But I can do the same elimination for all of them. So the same way I can get the Cj minus 1 is 0 and so on till C1 is 0. So indeed, from this assumption and from the fact that the axes are eigenvectors corresponding to unique eigenvalues, I derive that this implies that all the C's must be 0, which means that the vectors, the eigenvectors, are linearly independent. Makes sense? So if we have, if we are in the nice situation that we have n eigenvalues which are all different, like in 3 by 3, I would have eigenvalues like 1.2, 5.7, and 6 or something like that, then we know that everything is cool, because then we know everything is cool because then we have linearly independent eigenvectors, and there is n of them. And if n is the dimension of the space that something interesting happens, then we can easily diagonalize, because then these eigenvectors will actually form a basis of the n-dimensional Euclidean space, which is very useful, very helpful. Basis, how was a basis defined? Remind me. Yeah.
The vectors needed to hit every point in space.
Correct. So yeah, they have to generate the space, and they have to be linearly independent.
Yeah.
Right? So if there's n, if the dimension of the space is n and they are all linearly independent, they already have to generate a, right? So the eigenvectors will indeed be a basis. So that means if I take any vector from Rn, I can write it as a linear combination of eigenvectors, right? Because it's a basis of Rn. Any vector can be written as a linear combination of the basis vectors, and in this particular case, I chose a special basis formed by the eigenvectors. whenever that's possible. It's not always possible, but quite often it is possible, and when it is possible, it's very useful. Because why it is useful? Well, watch this. So I took my vector x and found the coefficients with which I need to multiply my eigenvector basis, so I get exactly the x. So those are the y's are like the coordinates of x with respect to the basis. Okay. Now let's see what happens if I apply the matrix to the vector x, or just do the matrix vector multiplication ax. That's what I mean by applying, or like subject it to the linear transformation represented by a. So I do this, but because the v's are eigenvectors of a, the matrix is doing nothing but scaling the vectors v, because they are eigenvectors, right? That's what the action of the matrix on the vector is. It's just the scaling. So the application of the matrix is just scaling by a different amount in every coordinate, right? So that's what this lambda 1, lambda, those are the eigenvalues. But that's it. And if I repeat this, if I apply the matrix again, then I would just end up with taking powers of the eigenvalues there. Because if I apply it again, here I'll get lambda 1 again, so it will be lambda squared. Here I'll get lambda 2 again, so it will be lambda 2 squared, and so on. Yep. So this is already fairly close to diagonalization. So let's take a look how exactly it looks. So this is just repeated from before. So let's assume that A has unique eigenvalues and a full set of linearly independent eigenvectors. So they form a basis. So we can write this formula. This is just the expression of x in the coordinates with respect to the eigenvector basis. And I can write this in matrix form. If I put all the eigenvectors which form the basis into a matrix called V, so I stack them as column vectors like this, then I can just write this formula. This is a formula between two vectors, right? And I can write this as a matrix vector multiplication. So this is exactly the same formula as this, right? When I define the V to be the matrix, where the eigenvectors are the columns of the matrix. Okay. Now the great thing is that because the eigenvectors, as I just proved before, we assume that they have unique eigenvalues. That's one condition under which it's true that the eigenvectors must be linearly independent. Then the matrix is invertible. It also follows because its basis also must be invertible. So we can write that, we can also flip it, right? We can multiply it by V inverse, because V inverse is now well defined, and we can recover Y as V inverse X. Or this is how we get the coordinates to begin with. So this V inverse is essentially a change of coordinates transformation. If we give it, or extract the coordinates out of x, if we give it the vector x, it gives us the coordinates with respect to the eigenvector basis. And we could also interpret the matrix V as from the coordinates giving us back the vector, just doing the linear combination. So if we have that, you can see that in this basis given by the matrix V, given by the eigenvectors, the action of the matrix is simply scaling of the coordinates. So I can write it in this form. So V inverse X, that's what we were previously saying, was Y, right? Then this was, so this is basically, one way we can look at it is by looking at this formula here. So first getting the y's, then scaling them by lambdas. So here I defined a diagonal matrix lambda which has the eigenvalues on its diagonal. it's again n by n matrix. Everything here is zeros, zeros, and here are the eigenvalues on the diagonal. So that this means scale every single coordinate by its corresponding eigenvalue, and this v it then again multiplies with the v's to go back. So what this says is that if this is the case, so if we assume, for example, that A has n unique eigenvalues, then I can write the matrix in this form: some invertible matrix V, a diagonal matrix lambda, and the inverse of V. And this is called the diagonalization of the matrix, because sometimes it's also called that it's similar to this matrix, and this transformation will be like a similarity transformation. But the point is that we have converted it to like a diagonal representation modulo in some specifically chosen basis. The other way you can look at this equation, if I multiply from the right with v, so this is equivalent to saying that AV is V lambda. By the way, this capital lambda is just like to denote that this is a matrix of these lowercase lambdas, the diagonal matrix of all the eigenvalues. So this is obviously equivalent, right? This is just about multiplying it with V inverse or V, whichever way you want to go. And this equation, this is like a matrix equality. And if you look at it, the matrix of V's was just taking the eigenvectors as columns, right? That's all the matrix V is. And what is doing V lambda? V lambda is scaling the columns of V, right? So this on the right hand side, so this is, okay, I guess I could put like another equivalence, I mean like a logical equivalence. This is nothing but this. Oops. Can you still see it? Yeah, you can still see it. And this is exactly the definition of eigenvalues and eigenvectors to begin with, right? Eigenvalues and eigenvectors are defined like this. So this is really just the very definition. It just what is important here, that I can only take the inverse if this is an actual invertible matrix. So if that's the case, and that's the case, for example, where all the lambdas are unique, all the eigenvalues are unique, then I can do the diagonalization. Then I can do this. So let me show an example where this could be useful. Let's take a look at the particular and fairly interesting application. Have you heard of Markov chains? Okay, good. So this is, so you might also heard that eigenvalues and eigenvectors are important there, among many other areas. So this is an example using a Markov matrix or Markov chain. And we will use the diagonalization or eigenvalues, eigenvectors to reason about a steady state distribution of this Markov chain. So we will be looking at this example. This is the matrix. So as a Markov chain, so what is it modeling? It's modeling some stochastic system. In this case, the system, we draw it here. It's as simple as this. I put like here. So I have two states, S1 and S2, and I'm like an end or some sort of entity which can be switching between these two states, and there are some probabilities. So if I'm in state S1 with probability 0.8, I will stay in the state S1, and with probability 0.2, I will switch to state S2. Similarly, if I'm in S2, I have probability 0.7 to stay in that state, and probability 0.3 to go to S1, to switch to S1 back. Okay, so this is the Markov chain, I guess, the system that's represented by this matrix. Now notice, because these are probabilities, they have to sum to 1, right? Because if I'm making a transition, then I'm making a transition for sure. That's probability 1 event. So they have to sum to 1, right? Which is true. This is 0.8 plus 0.2 is 1, and 0.7 plus 0.3 is also 1, right? So I always make a transition with probability 1. So this is the system that is represented by this matrix. This is a Markov matrix because all these numbers are probabilities, or in every column there's a probability distribution, so they are all non-negative, and the entries in every column sum to 1. So they are really just transition probabilities in such a system. The intuitive I always find the reasoning about probabilities a little bit confusing, so you can easily attach to it like a very intuitive interpretation. Let's assume I have like million ants or some like small entities that can live either in this state or in this other state, and all their life consists in switching between the states. So at every step there are like discrete steps, like ticks of a time or something, beats of a drum or something like that. So every single ant rolls a dice, and according to these probabilities, either stays in the state or switches to the other state. So it like travels to a new one. Either it stays there or travels to a new one. And the idea is I have like a lot of them. That's what means the probability. And I'm interested in the following question. You have some initial distribution of ants. For example, I have 1 million of ants, and half million is in the left one, 500,000 is in the right one. And I let them do their job, let them do their work. What will be the distribution of the ants in these states after a long time? If it will converge to something, that's interesting. If it will, what it will converge to. So let's take a look. So if I have some initial distribution with x and y, so for example 500,000, right? After one step, what is going to be like? So if I say that the distribution after one step will be x prime and y prime, then what's going to happen? So how many will I have in S1? Well, 0.8 of the ones that already were there will stay, right? And I will also get 0.3 that transitioned from S2, right? Similarly, for the other state, I will get 0.2 coming from the first state, and 0.7 that just decided to stay there, right? That's the probability of the transitions. So this is exactly just taking this matrix A and multiplying the vector xy. So if I have like an army of ants, 500,000 in one state, 500,000 in another state, and I apply the transition, and I just do one step of that, then the distribution after the step will be just matrix multiplication of A times the initial distribution xy. Do you somehow follow? So then if I do it again, if I do another step, then I just have to do A squared, right? xy. And if I do 1,000 steps, all I have to do is take A to 1,000 and multiply with the initial distribution. And this is what we are interested in here. Interesting, if you simulate this ant population for long enough time, what will be the distribution in these two states? Like you can actually reason about it intuitively. What would you think, even without reading the rest, if you haven't already? So don't read the rest if you haven't already. So what does it look like? It's more likely to be in S1 than in S2, right? Because in S1 I have higher probabilities to stay in if I'm already there, and I also have lower probability of switching, right? I have a higher probability of going between S2 to S1 rather than going from S1 to S2. Also in S2 I have lower probability of staying, right? So more likely after a long time, S1 will be having more ants than S2. You would think, right? one way we could compute it, like you could have this as an interview question, right? And one possible solution you could say as good programmers, well, let's just simulate it, right? That would be actually very, very good experiment to try simulating. Of course, if I have million n's, then every step is sort of costly, right? Unless I figure out I can do it as matrix multiplication. But even then, it will be costly to find out what happens after like 1,000 steps, right? So what happens after 1,000 steps? We can use the eigenvectors to get the answer very, very elegantly. So what we have been looking at this matrix before, and we found that it has eigenvectors 0.3, 0.2, and 1 minus 1. Or I could say 0.6, 0.4, right? Doesn't matter because we know that eigenvectors are specified up to a scale, right? So if I want to find what happens after 1,000 times, all I need to do is to raise the matrix to a power of 1,000 and multiply it with the initial state distribution. This will get me fairly close to the steady state behavior. The steady state would be if this goes to infinity, but like 1,000 for this purposes is almost as good. And if I express x in the eigenvector basis, so these vectors are linearly independent, form basis of R2, then the multiplication by a to 1,000 reduces to just raising to the power the eigenvalues. So this guy had an eigenvalue 1, and this eigenvalue was 0.5, if you don't remember the example we were doing on Monday. So this was this exact matrix. This eigenvectors, and those were the eigenvalues, or this eigenvectors, doesn't matter. They just differ by scale. And as you can see, this is the critical difference. There is the 1 and 0.5. If I take 1 and raise it to 1,000, then nothing happens to it. It still will be 1, right? 1 times 1 times 1 times 1. It's all the time it's 1. But 0.5 raised to 1,000, that goes really quickly to 0, right? If I do 0.5 times 0.5, I have 0.25. If I hit it again with 0.5, then it becomes like 0.125 or something like that. It goes to 0 very quickly. So already after 1,000 steps, this will be almost exactly 0. It will be like 0.0000000, nothing almost. So what that means is that the steady state will be exactly described by the first eigenvector, by the 0.3 or 0.2. So if you want to make them, this is why I wrote here 0.6, 0.4, because I wanted to make it to sum to 1. It means that the steady state distribution will be 60-40. 60% in S1, 40% in S2. It sort of corresponds to the intuition I said that it's more likely to be in S1 than in S2. And the way we compute it is using eigenvectors, eigenvalues. And the cool thing is, if you really coded up the simulation, which you can do in MATLAB fairly easily, you should get the same result after running it for a sufficiently long time. Now, you know what is another very interesting thing about this? How does the initial state matter? So I was saying, like, to motivate that I start with like equal number of n's, like 500,000 in S1 and 500,000 in S2. What if it was different? What if I had, for example, 0 n's here and 1 million on the other state? What would change after 1,000 iterations? Nothing. That's the cool thing. The initialization x doesn't matter after long enough time, of course. All that matters are the transition probabilities there, which is sort of interesting. Okay, so this was nice. Unfortunately, it's not always so nice. Sometimes we have matrices that cannot be diagonalized. Even if I go to complex numbers, it's not gonna help me. Those matrices are called defective matrices, and they are characterized by the fact that they have repeated eigenvalues, but then they don't have enough eigenvectors. So maybe let's look at this one. Let me explain. This is the 1, 1, 0, 1. So if I do take the characteristic polynomial, it will be this, which is 1 minus lambda squared, right? So this has a double root. Lambda 1 is and lambda 2 both are 1. But when I try to compute the eigenvectors, then I just get this matrix. I subtract the eigenvalue 1, right? And now I'm solving for this. So all the eigenvectors have to satisfy this equation, right? Where the second one doesn't matter. And the first one just says that y is 0. And that's the problem. That means that all the eigenvectors here are only in the one-dimensional space alpha 0, where alpha should be non-zero. So this matrix will never have two linearly independent eigenvectors. We are screwed essentially here. This matrix is an example of what's called like a defective matrix, also cannot be diagonalized. So not all matrices are diagonalizable, unfortunately. The best thing you can do is Jordan normal form, but we will not go there. This would be another example of a matrix that's not diagonalizable, which does not have enough eigenvectors. Now what the problem is, it has to do with these concepts algebraic multiplicity and geometric multiplicity. So the algebraic multiplicity of an eigenvalue means how many times is it the root of the characteristic polynomial. Like here this 1 was a double root of the polynomial because it was just twice there. That's the algebraic multiplicity. The geometric multiplicity of an eigenvalue is the dimension of the null space of this system after I subtract the eigenvalue times identity matrix. It is true that the geometric multiplicity is always less than or equal to the algebraic one, but unfortunately sometimes it happens that the GM can be strictly less than AM. What's the example of this matrix, right? The geometric multiplicity of the eigenvalue 1 was just 1, but the algebraic was 2. So if this happens, we don't have a full set of eigenvectors, and therefore we cannot diagonalize. And yeah, it's just know that the problem was not that the eigenvalues are repeated. Sometimes they can be repeated and it's still fine, like in the case of a diagonal matrix, right? The diagonal matrix also has repeated eigenvalue 1. But in this case, we are fine because in this case, the geometric multiplicity is also 2. The algebraic is 2, and the geometric is also 2. So here we hit the equality, this thing here, not the inequality. So with the identity, it's fine. That is diagonalizable. It's diagonal to begin with, so it would be weird if it wasn't diagonalizable. But some matrices just cannot be diagonalized, even if we go to complex numbers. Okay, there are some good properties of eigenvalues. One nice property relates eigenvalues and determinants. Sort of nice. So if you don't have the bad matrix, I guess that's probably another motivation for SVD. Like SVD will not have any of these corner cases that like sometimes it just doesn't work. It just does work all the time. So we will get there. This is how we get there. So eigenvalues and determinants. If you have a diagonalizable matrix, then we can do this, where V is invertible and lambda is a diagonal matrix of eigenvalues. And we can easily relate determinant of the matrix to its eigenvalues. So we start with this property, which you should remember from the determinant part. How's the homework going, by the way? The determinanty homework. Nobody started yet, I suppose. So here we do like a little determinant exercise. So A is V lambda V inverse. So applying this property, we can just split it into these separate determinants and multiply them together. We also know that the determinant of an inverse matrix is the inverse of the determinant, right? That's the second equality here. But then this is just inverse of this, right? So it just cancels, it just falls out. So the determinant of A is exactly the determinant of lambda, but lambda was diagonal, right? Remember, lambda was this. Lambda was lambda 1, lambda 2, to lambda n, with zeros everywhere else. So that means that the determinant of A is just the product of the eigenvalues. It's an interesting property of the determinant. You can also see immediately from there that the matrix is singular if it has an eigenvalue 0, right? If it's an eigenvalue 0, then the determinant also has to be 0, because then they just multiply 0. Whatever you multiply with 0, you get 0. Yeah, we can probably still do the trace thing. Here's another cool thing about eigenvalues. This time it ties to matrix trace. You know what is a trace of a matrix? It's like, sounds very fancy, and it has cool algebraic properties, but it's nothing but the sum of the diagonal elements. So A is an arbitrary matrix. It has whatever elements here, and the trace is just the sum of the diagonal elements. As dumb as that. But interestingly, it actually has cool properties. Like, obviously, if I transpose it, so that's defined for a square matrix. Obviously, if I transpose it, nothing changes, because the diagonal of a square matrix doesn't change, right? So nothing really changes. So trace A is trace AT. It's a little bit more interesting that trace ATB is essentially a dot product of matrices. That probably deserves a little bit more explanation. So if my A is a matrix like this, it doesn't even have to be square, actually. So it has n columns and could have m rows. So this is A, and B would have the same layout. B would have B1 to B is the same dimensions. So if I do AT, I will get this. And then I multiply with, B1, Bn, and then I take the trace. So what the trace is going to be? The trace sums the diagonal elements, right? But here the diagonal elements are just AIT BI, right? A1 T B1, A2 transpose B2 up to N1 and AN transpose BN. So what that means is really just taking the dot products of all the columns and summing them together. In other words, it's really like a dot product of matrices. Like if I take the matrices and like put them together and multiply every element with its corresponding element in the other matrix and sum all the thing together, that's exactly what's captured by this formula. That's the trace of ATB. It's fairly important identity. In particular, if I use it for the case where B is just A, so trace ATA, this is essentially just a norm of a matrix. Again, it's just like a length of a vector, except it applied to a matrix. This one is so important, it's called the Frobenius norm. Sometimes it has a notation like this, like a norm with little f there to denote the Frobenius norm. And really it's just Euclidean norm applied to matrices. And I just must tell you this too, that there is this cool property relating trace and eigenvalues. Okay, let's see if I can explain that real quick. If it doesn't work, then I'll reiterate on Friday. So there is one property of the trace says that trace CD is the same as trace of DC. That follows directly from the definition just by shuffling the sums and the indices. And if I have a diagonalizable matrix, so I can write A as V lambda V inverse, then I can apply this property. And because V inverse V is identity, then I see that trace A is exactly the trace of the diagonal matrix of eigenvalues. as nothing but the sum of the eigenvalues. So that is cool. The trace of the matrix immediately tells me what the sum of the eigenvalues is, which is very interesting, I think, because the eigenvalues are sort of difficult to compute. You have to go to some like polynomials or do some funny numerics or call MATLAB or something. But to compute the trace, that's the dumbest calculation you can possibly imagine, right? You just take the diagonal elements of the matrix and sum them together. So this is something that's super easily computed, and this is something that's not that easily computed if you didn't notice the same thing, the eigenvalues. And you can use this as a check to see if you got your eigenvalues correctly. Very cheap check. Okay? I have to let you go now, but let me know if there is something you wanted to ask about.